Today we have Emil Martinec talking about a very profound philosophical topic, life and death of 5 brain stars.
Thank you. We on here? Okay. Right. So we're going to talk about today, the bulk of it is contained in a couple of papers from last fall in collaboration with Yoav Zigdon. But it's informed by earlier work that I've been reporting over the years at these conferences with Stefano Masai and David Turton. And roughly speaking, the division of labor is, this is a discussion in the context of effective field theory, where this is a discussion in the context of exact worldsheet solutions for string theory backgrounds. And we're going to play those two off against one another and try to get some kind of a bigger picture of what's going on with 5 brains in string theory. It's also informed a little bit by the stuff that I talked about last year at Microstates 5, and hopefully we'll have time to get there. I would say I'm gonna, because this is a specialized audience, I'm gonna skip over a lot of the introductory, not skip over it, but go through it quickly. If you want a more discursive version of it, I gave a similar talk at the Strings conference, at the String workshop in Santa Barbara recently. Now, I'm also going to try your patience by giving you the third talk about 2-charge BPS microstates, or it's 2-charge BPS states in the last 3 days. Hopefully my take on it will be a little bit different from Samir's and Ashok's. And I can't talk as fast as Yosef. So I have way too many slides prepared, so let's just begin. So why 5 brains? Well, the Novoshort's 5 brain is a really good tool if you want to study back reaction, because it's one of the heaviest things we have. It has, in string theory, it has a tension which goes like 1 over G string squared. And so necessarily, if you have a 5 brain around, it sources some kind of semi-classical, but typically stringy background. And so we'll use them to explore the stringy properties. We're after a bulk picture of the typical half BPS microstate. What we'll find in the course of that study is that in this particular duality frame, the half BPS states are not small black holes, but they're stars made out of 5 brains. And I want to use that to my advantage, because the kind of thing I'm after is what happens when that star collapses, okay? What are the new degrees of freedom that become available when you have a star made out of 5 brains and it starts collapsing towards a black hole? And in the course, we'll develop a picture of the 3-charge microstates that have been investigated by Nick and Yosef and collaborators over the years. And then I will just shamelessly speculate about what this means for black holes, but only when the time comes. So along the way, there are a variety of strings that we're going to encounter, and it's useful to keep them straight. One is the fundamental string. So eventually we're going to want to make ADS3, so we're going to want to bind fundamental strings to the 5 brains to make an ADS3 near horizon geometry, or near source geometry, I should say. We're also going to encounter the 6-dimensional effective string that you get by taking the 5 brain and wrapping it on T4 or K3, and that makes an effective string in 6 dimensions after dimensional reduction. And the properties of that effective string will be a large part of the story. And then eventually, if we want to study black holes, we need to think about what's called the little string that lives inside coincident 5 brains and whose non-abelian entropy is what underlies the thermodynamics of black 5 brains and BTZ black holes. Okay, so let's begin with a quick overview of the geometry that's sourced by a bunch of NS5 brains. So as usual with BPS things, you need a harmonic function that's related to the 5 brain source. And from it, everything else is a consequence, namely the warp factor in the transverse geometry to the fibrane, the dilaton, and the magnetic flux that's sourced by the fibrane. And long ago, this geometry, which is basically asymptotically flat and then dives into a linear dilaton throat at the scale that's set by the fibrane charge. Callan and Harvey and Struminger said, well, we'd like to study this in string theory. This geometry is too complicated. Let's make a simplification by taking G string to 0. So this is the first decoupling limit in string theory, well in advance of gauge gravity duality. But it has the nice feature that when you take this limit, basically you push the asymptotically flat region up to what we now call the UV, and the entire throat becomes this linear dilaton region. And so the theory becomes a linear dilaton for the radial direction, free field theory, some angular WZW, SU2 WZW model for the angular sphere transverse to the fibranes, and then the 5+1 dimensions along the fibranes. And so this is an exactly solvable theory on the world sheet. Note that this WZW model governing the angular sphere, for unitarity reasons of the world sheet theory, is required to have at least 2 fibranes, and that will be important for our discussion. Okay, but because of the linear dilaton, there isn't a perturbative S matrix in this background, because every string is either coming into a region of strong coupling or emerging from a region of strong coupling. So if you send a wave packet in, it just goes into some strong coupling region, and you lose track of it, and it never comes back. Now, of course, if you're a black hole person, you say, great, it gets absorbed onto the fibrane and makes some black thing, but we're going to want to avoid that situation for as long as possible in order to keep track of, in order to say as much as we can using perturbative string theory. And so how do we avoid this strong coupling problem? Well, it turns out that one way to do it is to separate the fibranes. So just pull them apart instead of being coincident. Let's pull them onto their Coulomb branch. And what was observed most forcefully by Givon and Kudasov almost a decade later is that if you put the fibranes in a ZN5 symmetric array, you pick some circle of radius A, you put the fibranes on that circle and some ZN5 symmetric arrangement, and that you find that there is yet another exact worldsheet solution for that background. But now the background, instead of having linear dilaton, is some tensor product of coset models. And in particular, what used to be the radial direction is now this famous SL2 mod U1 cigar conformal field theory, where the dilaton asymptotically is linear, but it terminates in some kind of capped geometry. And so there's a maximum value of the dilaton, which is basically governed by the separation of the fibranes. And so the naive supergravity geometry that you would get by just using this separate source harmonic function is completely unreliable at the scale of the fibrane separation. You know, a geometer would say, okay, I have this harmonic function, and the geometry that it's sourced looks like this, where there's the throat of N5 fibranes, but then I get to the scale where they're separated, and I would just dive into N5 separate little throats of string size. And that's just wrong. The exact string theory solution says the geometry basically stops here, and that a perturbative string coming down from the asymptotic region hits this region, basically sees the cap in the cigar, and then just bounces back. However, we know from the CHS solution that if we push any two of the fibranes back together, the throat of two fibranes exists as a worldsheet theory because of this fact that a level 2 SU2 WZW model is a perfectly sensible thing. And so the strong coupling problem returns if we try to push two fibranes together. And so the lesson is that as long as you keep the fibranes separated, perturbative string theory is perfectly reliable, but supergravity is not reliable.
Sorry, should I think of this as two different limits instead of one is wrong, one is correct? Because here, to get the picture on the right, you actually need to take a double scaling limit?
So the picture on, so these are two pictures of the same thing. This is the geometry if you ignored stringy effects and just said supergravity always works, okay? And what I'm saying is that no, the geometry that's seen by string theory is something else. And so it's, how to say this? The cap that's seen by strings is exactly the scale in the supergravity solution where you start resolving individual fibranes.
But I think to get the picture on the right, you actually, to take G string to zero limit, but in the same time, you also want to shrink the circle of the fibrane.
That's exactly what I'm doing in both cases.
But if I just take G string to zero, but do not shrink the circle, I will get the picture on the left, I think.
No, if you don't shrink the circle of fibranes at the same time as you take G string to zero, then all the fibranes just get pushed out of the throat altogether. Okay. So you are right that the limit that we want to take is starting from here is a limit where we hold G string. So we hold them separated. Where am I? We pull them apart, okay? And the point is you want to take the radius of this circle to zero with G string in the appropriate way so that what you're holding fixed, basically, because the throat has this linear dilaton, when you say that the dilaton has some maximum value here, that is the scale at which what you're basically trading is the scale of this VEV for the value of the dilaton at the scale of the fibrane separation. So that's the thing I'm holding fixed, okay? And one way you can think about what I'm doing is that, these are NS fibranes and you can stretch D branes between NS fibranes. So what I'm holding is the mass of the sort of W objects fixed in the limit that I'm taking. And so for that reason, Givon and Kutuzov called this double-scaled little string theory. Okay. Right. So now I'm going to torture the fibranes a little bit. So let's compactify them on a 5 torus. Let's twist the boundary conditions so that instead of having N5 separate fibranes, each of which wraps this circle once, I want one fibrane that wraps this circle N5 times. And then I'm going to want to add, so the problem with that is that if I tried to separate the fibranes and I did nothing else, the fibranes would shorten their world volume by collapsing back together. So in order to keep them separated, I need to excite some momentum carrying waves. The waves have the effect of jostling the fibranes in their transverse space and keeping them spread apart. And so what do I have on the fibrane world volume? Well, they're basically 4 scalars that say where the fibrane is in its transverse space. And then there's a tensor multiplet, a tensor gauge. If I'm in type 2A, there's a tensor multiplet that lives on the fibrane. And then there are their super partners. And okay, and so as I was saying, the momentum in these transverse scalars keep the fibranes wandering around, and so thereby avoiding strong coupling effects, provided that if the fibranes are self-consistently separated by enough, string theory will not see a strong coupling problem, even though, once again, supergravity will have a strong coupling, naively have a place that it naively everywhere where you see a little fibrane thread here, the dilaton is naively blowing up. And what I'm telling you is that what we know from the exact solutions, that that's a feature of supergravity, not a feature of perturbative string theory. Okay, so what is the typical geometry? It's again sourced by some harmonic functions. It's just now that we let the place where the fibrane is in the transverse space adiabatically wander according to some left-moving profile of wave excitations. And there's a generalization of the fibrane harmonic function. And in addition, there's the thing that tells you that the fibrane is carrying momentum. So precisely at this singular source, there's some stress energy that's carried by the fibrane, as usual, in the Ty cross term in the metric. And then there's also angular momentum that's carried by the solution, governed by some cross term between T and the angular directions. Okay, and Lunin and Matur originally got at these solutions by finding the taking the Dabelkar-Harvey solution for a fundamental string carrying momentum and winding, and chasing it through some sequence of duality transformations. And my attitude here is going to be that we should always work in the duality frame in which the effective supergravity is as close as possible to capturing the physics. Okay, so I don't want to just take the half BPS solution in some other duality frame and then dualize it. I want to work directly in this NS5P duality frame and construct the solution. So this is a little bit of a tedious exercise, but I think it's useful for where I think this program should head. And so we should write down the bulk supergravity. We should write down an action for the fibrane, which is basically its world volume, a sort of a Nambu-Goto-like world volume term, and then some coupling to the magnetic sixth form that's dual to the Nova-Schwarz B field. And so if we dimensionally reduce this both in the bulk and on the brane, we get some 6-dimensional supergravity action that's coupled to a 1+1 dimensional string. And so this fibrane action then reduces to effectively a 1+1 dimensional string action of the usual Polyakov form. And on that effective action, okay, there are 4 scalars which are saying where the string is in its transfer space in 6 dimensions. And then the internal gauge fields reduce appropriately as well. And so, okay, so you vary both the bulk and the brane action. You get some equations of motion. They boil down, as usual, to harmonic equations for the various harmonic functions I showed you before. And so everybody's happy. So these chiral wave profiles on this effective string parameterize the space of 2 charged solutions. And so, what we've learned over the years is that if you have a space of classical solutions, there's some symplectic form, and you can do geometric quantization. And here, this just amounts to doing the quantization of this effective string in the usual way you would quantize a string. So one of the things you learn when you study first quantized string theory is that there's a reparameterization constraint, so-called level matching condition, that relates the difference in the number of left-moving and right-moving excitations to the momentum and winding that the string carries on this circle that it's wrapping n5 times. And if we want a BPS solution, then we should set the number of right-moving excitations to 0. And so all of the entropy of 2 charged solutions comes from how do we partition this total excitation level among the various oscillators on the string world sheet. And so one question you might want to know is, what does the typical such 2 charged state look like in space-time? And so for that question, what I'd like to do is to construct the ensemble average. So, if this were a black hole, we would say, okay, let's look at the sort of typical, what is the Schwarzschild geometry? It's what I would call the ensemble average of all of the black hole microstates. And so follow the same logic here. We would say, okay, let's construct the maximally mixed state on the space of half BPS configurations. And let's just take these harmonic functions and construct their ensemble average. And since, of course, the harmonic equation is some linear thing, we can superpose solutions, and everybody Nobody should complain. And so this was done, by the way, quite a while ago by Alde de Boer and Messima. Basically, we sort of got halfway through this project and realized that it had been done before. But they were confused by a few things, and so I think what I'm about to tell you kind of cleans that up. So, okay, so we have this effective string, and it's convenient, instead of trying to fix the total oscillator level, to just fix some left-moving temperature for the oscillator excitations. And then, as I say, do this trace over the half BPS Hilbert space to average the harmonic forms and functions. And, oops, here we are. And so what does that mean for the effective worldsheet theory? Well, this effective string that I'm getting by dimensionally reducing the phi brane on T4 has a tension, which is basically it has an inverse tension, which is G string squared, because it's a phi brane, and then V4 from the fact that I'm compactifying it. And so that gives me some kind of effective alpha prime of this string. And so that's going to set the scale for whatever solution I'm getting. And then the trace that I'm doing just becomes some standard Hilbert space trace, which becomes a torus path integral over this effective string. So, okay, so I do this torus path integral. I'm interested in evaluating this harmonic function. So to process it into something which is more convenient for string theory, I do some kind of integral transform to make it a torus one-point function of a standard string vertex operator. And so if you, okay, do the path integral, carry out the integral transform, you find, and then furthermore do the Legendre transformation from working at fixed inverse temperature to working at fixed level, one finds that the average of this harmonic function basically looks like the extremal black hole harmonic function if you're at scales which are much larger than some fiducial scale R sub b. And then once you get to that scale R sub b, the singularity in the harmonic function starts to shut off. And by the time you get it to the origin, there's an x squared from the numerator that cancels the x squared from the denominator. So this average geometry is completely smooth. And so there's some kind of blob of radius RB. The geometry outside that blob looks exactly like the massless, looks like the extremal phi brane, the CHS solution, but then you get to the scale where the phi branes are separated and it starts looking different. Okay. Now what sets this scale R sub b? It's that I have a thermal gas of left movers on this string. And so the string is wandering around in 6 dimensions. And so it's coherent over a thermal wavelength of this effective temperature. And so I should just ask, and we know from work in the 80s that a highly excited string is basically a random walk. And so I should ask, how many steps are in the random walk? Well, it's however many thermal wavelengths there are as I go along this string. And the answer to that is square root of n. And so I should expect then that the typical transverse width of that harmonic, that random walk is the square root of the number of steps, which is this scale n to the 1/4. And then the thing that sets the overall dimensionful scale is this effective string tension. So everything about this solution is perfectly understandable from this picture of the phi branes random walking in their transverse space. And so if we look at things like the size of the transverse sphere, the transverse sphere is kept puffed up by the fact that there's this magnetic free-form flux going through it. But as we start diving inside this blob of phi brane, Gaussian sphere encloses less and less phi brane charge. And so there's less and less flux there to support the angular S3, and it starts shrinking. And of course, then by the time you get down to the origin, they're basically enclosing no phi branes. And so the thing just caps off smoothly. The 3-sphere just caps off smoothly at the origin. Conversely, the momentum of these scalars is pressure on the circle that they're moving along. And so the proper size of the Y circle is expanding as you get inside this blob, and it reaches some maximum scale at the center of the blob, which is parametrically large in the amount of momentum. So I call this a fibrane bag of gold because sort of out here, you know, way far away, it looks like you have some kind of extremal fibrane, but you get very close to it, you know, inside this blob, and all of a sudden there's a big piece of space. And there's a maximum redshift. The geometry is capped off, and again, it's determined by the competition between the two charges that the system carries. Okay, but I should say, this whole thing, this bag of gold, this scale R sub b, was something that was confusing to Alde, de Boer, and Messima. They kept wondering, well, you know, we were told that these things were fuzzballs, and that we count the fuzzballs by, you know, putting some kind of stretched horizon around them, and, you know, the area of that stretched horizon should be counting the number of fuzzballs. The problem is that this scale R sub b is like n to the 1/4 bigger than that scale. So what this is telling you is that at least in this duality frame, these things are much, much larger than any kind of stretched horizon scale. They're well outside what you would call their Schwarzschild radius. So they really are fibrane stars and not small black holes in this duality frame. And so this is where the discussion departs from the two other talks you heard on Tuesday. Okay. Now, for this picture to be self-consistent, I should convince myself that the fibranes in these generic configurations are indeed well separated. And,
so can I
yes.
here? So this violates this scaling that Ashok was talking about in his talk? And is that because...
It might. So I actually went back and looked at Ashok's paper on the two-charge solutions.
I was going to ask whether it's because this is a magnetic charge.
He assumes non-singularity of the geometry. And so here I'm explicitly saying I'm not scared of singularities in the geometry. Right? The naive, you know, all of these geometries look from the supergravity point of view like they all have fibrane singularities, and you would say, ah! And what I'm telling you is that what we know from these exact worldsheet solutions, that as long as the fibranes are pulled apart under their Coulomb branch, that's not a problem. And we can just count fibrane configurations.
I see. So it's not to do because of some electric versus magnetic or anything like that?
There may be something to do with the scaling that Ashok was... I actually haven't thought carefully about that, but that is an interesting question as to how this discussion comports with Ashok's scaling argument, but maybe that's a discussion for the break. Okay. So as I was saying, we want to be able to draw on our knowledge from the exact solutions, and the exact solutions were telling us that everything is reliable as long as the fibranes are separated. So we should go back and check in this generic random walking fibrane, does the random walk ever come close to intersecting itself, in which case I might worry that there's at least some regions where there's some strong coupling problem. And so the answer for that is no, and it's basically because it's a random walk in 5 spatial dimensions. And so random walks don't self-intersect in 5 spatial dimensions. And so if you compute something like the pair separation between 2 points on this random profile, this was something that we did in one of the papers last fall. And you can see that the average separation peaks around the scale of the blob and goes smoothly to 0. And if you ask, you know, what's the sort of area under this curve where you would stop trusting the solution, the answer is that it's parametrically suppressed in n. Okay. Now, there are 2 other things I should mention. One is there's this same ensemble was studied somewhat later by Raju and Shrivastava, and they argued that there are large fluctuations in these things, and they interpreted the fluctuations that they were computing as being some kind of quantum fluctuations, and so all of these geometries I'm telling you are somehow highly quantum and you shouldn't believe them, and classical physics is garbage. And so you have to be careful, because you're making an ensemble average in the maximally mixed state, as to whether if you compute some quantity like, say, the square of the five-brane harmonic function divided by its expectation squared as some measure of fluctuations, you should ask yourself, are the fluctuations you're observing when you do that statistical fluctuations of the ensemble, or some indication that the object you're looking at is highly quantum? Okay? And the answer, if you think about it a little bit, it's pretty clear that what you're seeing are statistical fluctuations. Because, I mean, if I take my water bottle and I put it here, and then I superpose it with another solution where it's over here, and another one where it's over here, then it might look like the fluctuations of my water bottle are enormous. But obviously that's because I looked at something which was big and heavy, and I try to make a quantum superposition of that. As soon as I kick it, it will decohere into a bunch of things that are all classical. And so this calculation that they did was some indication that this five-brane random walk is pretty squishy. It has lots of fluctuations. The typical one is not just this spherically symmetric solution that I gave you, but it has lots of multiple moments that are indications that it's pretty floppy. And so just to convince ourselves, what we did was we took this round solution that I mentioned earlier, and we studied it. We looked at that and asked the same question in a single. So to diagnose whether this is statistical fluctuations or quantum fluctuations, one thing you can do is pick a particular element of the ensemble and ask the same question. And so we did that for this particular round solution that everybody likes to study. And what we saw was that until x1 and x2 are basically Planck scale distance from the five-brane source, this is tiny. And so that's what you would expect, right? I mean, from this effective string picture. You usually trust the classical geometry of a string until you get to within a string length of the source. And in this case, the string length of the source is something related to the Planck length, because it's a five-brane. Okay. I think somehow I missed it. Here we go. Yes. I should have mentioned that one of the things that helps us to understand what's going on is that you can add this second charge. This is one of this solution is sort of like the canonical round two-charge solution that many people have studied over the years. And one of the things that is helpful in the present context is that Stefano and David and I have been exploring the properties of a closely related worldsheet theory, which again is a Gage-Wessamino-Witten model, which realizes this particular two-charge configuration. And so everything I said about the double-scale little string theory has a variant where you add the second charge and realize it as a Gage-Wessamino-Witten model. Okay. Okay, because it's an exact worldsheet theory, you can take that exact solution and you can t-dualize it. And the t-duality just ends up being some minor modification of the gauging of the Wessamino-Witten model. And so this same sort of Gage-Wessamino-Witten model also works as a description of the t-dual solution, where if we have five branes that are wrapping this circle and we t-dualize, they remain five branes. But the momentum that's keeping the thing supported t-dualizes to string winding. And so everything I just told you about five branes being puffed out is also some statement about the near source structure of NS5F1 solutions. Because if it's perturbative string theory if perturbative string theory is a reliable guide for the NS5P solutions, it's also a reliable guide for the NS5F1 solutions. We just need to be a little bit careful about what's the appropriate duality frame to be thinking about. Okay. Am I doing on time? Oh, not bad. So when you do that T-duality, in order to do it in supergravity, we need to smear the harmonic functions a bit, but that's okay. Again, everything is linear. And the dualization of the NS5P solution now becomes an NS5F1 solution. So now the Ty component of the metric becomes a Ty component of the B field. And now we have an electric H flux as well as a magnetic H flux. There's now a redshift that in the geometry that's governed by the peak in this harmonic function, which is secretly carrying the T-dual momentum flux. And so I continue to draw pictures like this, but you should keep in the back of your head that this is a picture of the NS5P source, and that anything you say about this should be processed through a T-duality along this direction. Okay.
So Emil, can I just ask something?
Yeah.
This T-duality, so if you didn't have this T direction, if you just had the original cigar, this T-duality is the one that makes it into a trumpet or something?
Yes.
Okay.
Yes.
So here there should be some trumpet and KK monopole, something like that?
Yeah, it's subtle.
Okay.
Okay. It's you have to be careful because the direction you're T-dualizing is partly, so the fibranes are, it's most convenient to look at this nice round solution because then everything's very clear. And what's going on is the fibranes are wrapping some direction which is sort of partly along the direction you're T-dualizing and partly wrapping some fictitious transverse circle. And so the thing you get after the T-duality is some mixture of KK monopole and fibrane. And the fibranes are stay fibranes because the charge you measure at infinity is still fibrane charge. It's NS5F1, not KKM-F1. And but the way to read this is that as you go around this circle, you cross N5 fibranes. As you go this direction, you cross K. What is K? K is basically a discrete parameter in the identification, which says that as I go up along a strand of fibrane, I hop over K fibranes and then make a periodic identification. So it's the pitch of the spiral, okay? And so as I cross, as the direction I'm T-dualizing, I cross K fibranes as I go up this way. And so what that tells me is that I'll have K KK monopoles that are nearly coincident in the T-dual geometry. And that's the structure of the NS5F1 supertube. It's a ring of fibrane that also has some KK dipole charge. And the KK dipole charge, the fact that you're crossing K of them is near the core of the thing, there's some ZK orbifold singularity. So this geometry that you actually get is not ADS3 cross S3, it's ADS3 cross S3 mod ZK.
You don't get a trumpet.
But you don't get a trumpet. The trumpet is the fibrane, right? The fact that the metric is blowing up near the fibrane because of the momentum is the analog of the trumpet.
I see. And so a related question, so on the worldsheet theory, again, without this T direction, I mean, if you naively, I mean, as you know, the correct way to do this would be to introduce some sine-Liouville mode or something like that. That's the dual, right? So is there some analog of that here?
Yes. Yeah. So there's a phenomenon called FZZ duality.
Yeah, exactly.
Okay. And what FZZ duality is the statement that associated to this geometry, very close to the source, is some kind of string winding condensate.
Exactly. So
The string winding condensate is the F1 source.
right. So when
Carried
I'm
by the
asking is, can we
fibranes.
write such worldsheet theories including with this twist, with this new?
this is the worldsheet theory. That gauge-Wess-Mean and Woodland model is an exact worldsheet description of this background.
Say, when the gauging was just, when there was just the usual cigar geometry,
Yes.
then we know what the FCZ duality is.
Yes.
I'm asking if we know it here.
Yeah, we do, because FCZ duality is just, it's really a property of SL2 conformal field theory. So the fact that you have this SL2R sitting here, FCZ duality, the parent of FCZ duality in the cigar geometry is a corresponding phenomenon, is a quantum equivalence in the representation theory of affine SL2 conformal field theory.
You can follow that.
And then you can follow that down.
Thanks.
Okay, so what does the thing look like? Well, if you're far enough away from the source, well outside what we call the string charge radius, you still have the throat of N5 fibrane, so it's linear dilaton. And then you reach the scale where you start sensing that there are strings around in the background, and it rolls over to an infrared region, which is ADS3. Because the Y circle was getting big in the original NS5P frame near the source, it's now getting very tiny as you get close to the source in this frame. And so there's a kind of a cusp in the geometry, which again is not very reliable in supergravity because the curvatures are really large here. Okay, and so this cuspy singularity is resolved by the fact that perturbatively, you should really be thinking about what's going on near this source. The T-dual Y circle is getting very small, so you should really look at it in the original NS5P frame where it's big and puffy. And so roughly speaking, what the geometry looks like is something which is ADS3, but then the Y circle gets really tiny in the core, and you should just really mentally go back to the original duality frame once the size of this Y circle gets below string scale. That happens at a radius which is well outside where the fibranes are. And so there's this, what I was calling the fibrane bag of gold, really is like a bag of gold now, because you thought you had an NS5F1 geometry, and all its microstructure is hidden in some kind of T-dual description, which is unavailable to supergravity, but perfectly well described in perturbative string theory. Okay, so now slides start appearing in yellow highlight because these are things that are not yet completely worked out. So warning signs whenever you see yellow. But having this picture of what the generic two-charge solution looks like, we can ask, what about this zoology of three-charge solutions that people here have been working on? And the answer, I think the answer to that comes from how they're constructed. So how do you construct these horizonless three-charge solutions? Well, basically you start with a horizonless two-charge solution, and then you decorate it with some kind of supergravity wave. And the property that you demand of that supergravity wave is that it's non-singular at the supertube source. In fact, you ask it to vanish at the supertube source. So really what it looks like is that somewhere further up the throat of the geometry, you've added some kind of supergravity momentum wave, which is circulating around in the throat and doesn't really touch where the fibranes are. And so that's why I like to say it's more like a toupee than hair, because it's not really attached to the fibranes. Masaki counted these things and estimated that in a particular regime where the momentum charge is large relative to the string charge, that you get sort of the two-charge entropy multiplicatively enhanced by the amount of momentum. And I should say that's maybe a bit of a surprise, because you might have thought, okay, if all I'm doing is taking a two-charge solution and then putting some gas of gravitons outside it, I would expect the entropy to be the entropy of the supertube plus the entropy of the gas of gravitons. But this gas of gravitons knows about the supertube because how does it know about the supertube? Because you demand that the supergravity wave vanish. So there's an effective infrared boundary condition that this wave has to satisfy. And so every wave is different by which random walk it's vanishing on. So if you pick a random walk, you can decorate it with a wave, but you demand an infrared boundary condition that that wave vanishes on that particular random walk. You pick a different random walk, and the supergravity wave has to differ because now it has to vanish somewhere else in this wiggly source. Okay. But I think the geometry might look something a little bit like this then, where you say, okay, there's this T-dual 5-brane bag of gold, and then there's some momentum wave that's sitting outside, and then once you get in the vicinity of where this momentum wave, it starts puffing out the Y-circle to some big size, and then you have an ADS2-like throat that then once you get to the scale of the momentum charge, asymptotes to ADS3. Okay. So one of the reasons I was interested in developing this effective action formalism is that it's going to be the most I think it's going to be the most useful way for addressing the question of what happens near the BPS solutions. And for this, the intuition that I'm following comes from the way we treat other solitons. You should really think of the 5-brane as it's the magnetically charged object of closed string theory. So it's like a soliton. It has a tension that goes like 1 over the string coupling squared, like a magnetic monopole in Yang-Mills-Higgs. And what is the near BPS dynamics of multi-monopole solutions in gauge theory? It's that you construct the nonlinear sigma model on the moduli space of multi-monopoles, and you do some kind of collective coordinate quantum mechanics in those variables, okay? So the natural analog here is that I have a multi-5-brane configuration, and we know it's classical configuration space. I just showed it to you. And so we should take the effective supergravity action and start doing a derivative expansion of it in derivatives with respect to the other light cone coordinate u. And so that derivative expansion gives me an effective field theory that as long as I'm in the part of the configuration space where the 5-branes are well separated, should be some kind of nice slow dynamics of near BPS, at least half BPS configurations, and if we could do something similar for superstrata, near BPS superstrata. Okay. And so where do we end up? I think there are two possibilities, and I don't know how to decide which of the two is realized. One is, well, so let me give the one which might be the most interesting. You might say, well, if I put on some excess energy, well, then I'm no longer BPS, so the gravitational attraction of the 5-brane starts exceeding the repulsion due to the B flux. And so you might say, okay, the thing wants to collapse. And how could it collapse? Well, something that I haven't been talking about very much are these internal gauge modes. And really, when I say there's some momentum charge that the system is carrying, it's partitioned between the internal gauge modes and these external scalars. But it's only the external scalars that keep the thing capped and smooth. And so if I start taking my excitation energy budget and start transferring some of it from the transfer scalars to the internal scalars, then what happens is my wiggly random walk has fewer steps. And so it's less puffed. And so the harmonic functions that you see that are governing the solution have some typical transfer size, which as I decrease the amount of excitation budget in the transfer scalars, gets more and more compact. The harmonic functions get more and more peaked. The throat gets deeper in length and larger in redshift. So this procedure of taking the total excitation budget in the NS5P frame and reorganizing how it's partitioned between transverse and internal scalars is a natural process by which this 5-brane star could collapse. And this would be, but slowly, right? So we hope to be able to follow sort of adiabatically some kind of core collapse of the 5-brane star. But another possibility is, when I'm doing that, I'm basically saying I'm going away from the sort of generic state. If I'm starting to put all of the excitation budget over here, I have to give up some entropy to do that. And so another possibility is that the system just, like a star, right? It just, if there's no gene, the question is there a genes instability? Because if I just had a gas, and I say try to compress the gas, there's less free energy if I try to put it in a smaller volume. It would want to spring back. So there's some kind of sort of, I think, natural thermodynamic calculation that's going to tell us, does this thing want to collapse? Does it want to stay a star and just have some, just be a slightly smaller star if I make it non-extremal? It's an interesting question, and we're gearing up to do that calculation. But if it does collapse, where does it end up? Well, it ends up that if you transfer basically all of the excitation energy out of the transfer scalars and into some internal excitations, you're back to this situation of nearly coincident fibranes and the strong coupling problem that I hope to avoid. But I think that's where, it's sort of like manifestly in this picture, that's where the black holes are. And so we should not be scared anymore of going there. And ask ourselves what the natural outcome of that collapse process is, and we should expect it to be some kind of black fibrane. And the black fibrane is governed by this same cigar geometry, except instead of the angular direction of the cigar being some spatial direction, it's now the Euclidean time direction. The fact that the throat has a radius square root of n5 is a statement that the equation of state of black fibranes is a Hagedorn equation of state, but not with an inverse tension, which is the fundamental string tension. It's something called the little string tension, which is n5 times smaller than the fundamental string tension.
So just a comment, aren't you being a bit wicked here? Because what you're doing is you're taking all this energy and excitations that you've represented geometrically in terms of motions of fibranes and shoved it into what you've called an internal degree of freedom, which you haven't treated in back reaction.
Nope.
And we know that thing sits on the torus and it's going to fatten out the phase space on the torus.
Yeah, I will refer you to Yosef's talk on Tuesday.
So I don't think it's going to go that route if you treat it back reaction.
Okay, so let's have that discussion in 10 minutes. To my mind, so from the effective action point of view, there's sort of like two ways that the system can carry the charges. One is this sort of collective motion of the fibranes in the ambient space, and the other is through these internal excitations of little strings. And those are two completely different things. So for instance, if you trace through how the KK dipole fibrane thing in this duality frame carries the string charge, it's a very pretty analysis of Gregory, Harvey, and Moore that says that there's some gauge mode, there's some Kaluza-Klein gauge mode that's sort of trapped near the source, and you analyze the dynamics of that KK. It's very much, again, the intuitions with magnetic monopoles are uncanny. It's very much the way that a magnetic monopole spins up to make a dion. There's some gauge mode in the core, there's some collective coordinate degree of freedom, you spin it up, and the momentum in that internal mode is the string charge. So that's one way the system can carry fundamental string charge. The other way it can carry fundamental string charge is that there's a term in the fibrane effective action which is just directly a B2 wedge F. And so if there are gauge instantons, and this is the way that Dijkgraaf and Verlindes were thinking about it back in the day, is that if there's some kind of non-abelian instantonic configuration, then that also sources a B2. And so that's a completely different way that the system can carry string charge. And once you have the string charge, of course, there's an effective description of it where it can also carry momentum, because an instanton in the 5+1 dimensions of the fibrane world volume is a string. That's this third string that I was talking about. So there are different ways that the effective field theory can carry the charges, and I'm saying that the way that supertubes and superstrata carry charges is completely different from what I think is the dominant piece of the entropy. But that's where you guys seem to be headed as well in talking about these M2, M5 intersections. So I think everybody should be happy. Okay, just one.
Just one question. So if
Yes.
you have more excitation energy, then you will get away from the regime of little strings?
No. I think the way I would say it is the reverse. That coming back to this picture. As I said, it's linear dilaton above some scale that's set by the string charge, and then it's ADS3 below. So if the horizon is out here, it's little string theory Hagedorn thermodynamics.
Yes.
If the horizon is in here, it's BTZ, because it's ADS3 black objects.
Then you have anything intermediate?
Yes, there's a continuous interpolation, so that's what I was just about to get to. If you take the Hagedorn equation of state of the little string with its appropriate tension, and you say, I'm going to ask that the little string carry the winding and momentum charges of the background, and I just take this naive formula for the entropy of a string-like object in 6 dimensions, and you take the limit that we want, the ADS3 limit, which is to take the radius of the circle big, so that the ADS3 region now covers everything. Then this entropy, black string entropy formula becomes the BTZ entropy, very directly. And if you don't take that limit, Ry goes to infinity, the thermodynamics just smoothly interpolates between high energy little string dynamics and low energy BTZ dynamics. Okay. So I see I'm just about out of time. So then the question is, then what? Okay. So I think if you're a supergravity person, you would say, well, okay, fine, a horizon, what we would effectively call a horizon is forming, right? Because the fibranes got close enough together that the non-abelian excitations were liberated. We saw that starting from the fibrane star. As the fibrane star collapses, the fibranes get closer together. The non-abelian excitations are still massed up, but they get less and less suppressed until eventually they get liberated. And this is something that we've understood now for 25 years, that the black hole phase transition in the brain in the bulk is dual to some brain dynamics where non-abelian brain degrees of freedom get liberated. And so Hawking-Page is the same thing as deconfinement. And what I'm saying here is that we're just seeing very geometrically in the fibrane dynamics when that deconfinement transition happens, it's when the throat gets deep enough that things start looking like they have a horizon. And so the question is then, at that point, what happens? A supergravity person would say, oh, there's no hope. All this stuff just collapses, crashes into a singularity. And the question is, can we include enough stringy degrees of, there are stringy degrees of freedom that you're ignoring in that supergravity, namely all of these stretched branes between the fibranes. And the question is, does that light dynamics save you? Does it take over and replace a horizon with something else? And the whole idea of the fuzzball program is, yes, that something else is the non-abelian dynamics of the light objects on the fibrane that you're ignoring when you do supergravity. There's much more to say, but I would like to believe that maybe this effective action picture can be extended a little bit beyond where you might stop trusting it, and just say it wants to be the membrane of the membrane paradigm. It's this little string gas is, it only starts appearing when the horizon forms, and it's clear that it's associated to the fibrane dynamics, and the fibranes are way down near where the horizon is. And so there might be an effective field theory picture, which is kind of a sort of a souped up version of what people did back in the day when they were computing black hole emission and absorption from brains. Namely, you say there's some brain dynamic, there's some stringy dynamics on the brains. You drop a graviton in, it becomes part of the brain gas, and then it emits. And so there were calculations by Callan, Maldacena, Das, Matur, et cetera, these people, right? It's saying that something gets absorbed into the brain gas and then re-emitted, and that's the Hawking process. And I'm saying, I'm posing the question, can we do that in a back-reacted version where there are degrees of freedom in the throat, they get absorbed into this little string gas and then get re-emitted? And you might, so there's lots to say about that, but I'm unfortunately out of time. So let me just throw up some conclusions. So I hope I've convinced you that we can learn a lot about the NS5F1 and NS5P systems by the use of some effective field theory. And in that effective field theory, it's pretty clear that the fibranes in this regime of configuration space are some kind of fibrane stars. And the pathologies in supergravity are resolved in string theory, but sufficiently strong perturbations are expected to collapse this thing. And then the question is, can we still use the effective action formalism, basically integrating in these new light degrees of freedom, and still have a useful picture of unitary dynamics in the near BPS black hole regime? And with that, I thank you for your attention, and that's it.
Just a quick comment. I mean, Emil's this liberation of these new link-like little strings. Emil's sick and tired of me probably saying this. It's what I call the coherent state mantra. There's a staggering number of microstates in these little strings, and once again, there are going to be coherent expressions of those staggering number of microstates. And so part of what Joseph was talking about in his talk was precisely you can look at various pieces of coherent pieces of the twisted sectors. So when you see something like that happening, you can still ask, what's the supergravity description of a coherent ensemble of them? And it looks like there's a large number of samples of that phase space. So I think this is really thought-provoking. Anyway. Anybody else?
Other questions? Comments?
Okay, I mean, this is something we've talked about already this week, but it's a question. So the fact that the five-brain star is so large is reflecting the fact that the whole ensemble of all the states includes states which are much bigger than the would-be stretched horizon of the two-charged black hole given its microscopic entropy.
Yes.
And also many states which are about that size. And so part of your story was that although the full ensemble geometry is much bigger than a black hole, it seems that contained inside the system, there are states which look very much like a small black hole.
Yes.
And so I wonder if there's a refinement of the calculation to exclude those long wavelength, much bigger states, and ask if there are other types of ensemble geometries that with restricted ensembles that may be much more complex.
Yeah, the simplest thing is to just have two temperatures, right? I mean, it's free gas of left movers on this string. So you're free to have one temperature for the internal gauge modes and another temperature for the external scalars. And so by dialing those, you can particular dial between these things that look more like small black holes and things that look more puffed up. That's one thing that one can do. And you know, I think part of this question of what happens with the near BPS dynamics is, you know, for instance, can you see that transfer of thermal excitation taking place? I should say one thing that also intrigues me about this setup is that, which has to do with entanglement. So there were one set of profile functions. There's just some scalars f of v, right? And those scalars appear both in the five-brain world volume action as the scalars on the five-brain, but they also parameterize some particular modes in the throat in the supergravity action. And so it's not like you could worry, am I doing some kind of double counting, right? Because in gauge gravity duality, you know, we're always taught, well, either you're doing the gauge theory or you're doing the gravity, and to have both of them around at the same time is some kind of double counting. But in this half BPS configuration space, it's that they're not independent degrees of freedom on the brain and in the bulk. And the FZZ duality that we were discussing earlier is an example of that. There's only one state, and in FZZ duality, in the cigar, sine-Liouville type duality, they're really two separate. There are two things that you might have thought are separate, but they're part of the same state, namely a string winding condensate at the tip of the cigar and some bulk geometry. And so this is some souped up version of that. That there's a string winding condensate that lives on the fibranes, and then there's some supergravity that lives in the throat, and they're all the same degree of freedom. So you can't like wiggle one and without wiggling the other. And so I think part of the question of what's happening in the information paradox is this entanglement between stuff in the throat. Where would I like this to go? It's that there's some thermal atmosphere outside the black hole, right? But then there's this gas of stuff that's living on the fibrane. And so it's not that they're two separate things and there's some Hawking process. No, it's that the Hawking quanta that are in the thermal atmosphere in the throat are highly entangled with this brain gas. And when you sample that thermal atmosphere and start, drawing stuff out and dumping it into a bath, you're selecting, standard quantum mechanics. You're selecting from some entangled state where the, one qubit represents both the Hawking quantum and what's left over in the brain gas. And so when you select it from the thermal atmosphere, you select some particular piece of the less excited fibrane state. And that's how the Hawking process happens in a microscopic theory. And the question of whether there's some kind of geometric interior or not, I'll leave for you guys. I don't understand it. Is there some kind of fancy map from which one can reconstruct a geometrical interior? That's beyond the scope of effective field theory. And right now, there's enough to do with the effective field theory.
Okay, I think that's a good place to stop. Oh, sorry, Ashok had one question, maybe last question.
Just a small comment that if we look at the index calculation that Samir and I described, the horizon size actually is much larger than the stretched horizon size.
Correct,
so it could be related to this, right? Because horizon size scales much larger. So I don't know whether that's related to this.
Okay.
Okay, we should talk about this.
Yeah,
Yes,
Euclidean,
yes.
exactly. Yeah.
No, but it would be interesting.
Yeah, it's not clear what the relation is, but nevertheless, this is just an observation that the actual horizon size of the Euclidean solution is much larger than the stretched
It would be interesting then to compare parametrically how it depends on the charges and see whether, if you trace your, I presume you could trace your solution through some duality chain and see what it looks like in this duality frame.
Exactly, yeah.
That would be interesting.
It should be easy, right?
Yeah.
Yeah.
Okay, very good. So time for coffee. When should we meet? 11:35. We meet again. Let's thank Emil again for a nice talk.